Today we do a transient analysis. So even linear component, when you apply the step function or non sine wave type of power supply, then it cannot be solved linearly. You have to use transient analysis. The circuit is, the simple one is C connected to step function. Okay, so R and C. So this step function is from 0 to V, and what's happened to this voltage? Okay, so the current is Ri. If current is I, it's Ri plus 1 over C I dt. This is E here, and this voltage across the resistor is going to be V, right? So we have to solve this equation. Now step function after voltage applied is constant. It's V0. So if you take a derivative on both sides, di dt plus 1 over C I equals 0. So this differential equation, this simple case, we can just directly solve it. Move this side and divide by I. Di dt divided by I equals RC 1. And this 1 is going to be, if you take integral, log I RC t, right? So I is plus C0. If you take an integral, you need the initial condition. So I is going to be A E minus T RC, and here RC we call the time constant tau. So using this I, E equals 1 over C I dt. Okay, so RC negative, right? And A E minus T over RC. And this A is initial condition. When you apply initially, we should determine this initial condition here. I, the first time when I apply this short circuit, so I is going to be V0R. So we apply that, and this is a time constant. C V0R, and this is time constant again, E minus T tau. So equation we need C0, this initial condition, when you take integral plus C0, right? Right. So minus V0 E minus T tau plus C0. remember to add the constant whenever you take a integral. So the initial condition for E is 0, because when you turn on, capacitor is pretty much short circuit. So V is 0 initial condition, right? The E is 0. So 0 equals minus V0 T. This is 0, so this is 1 plus C0. So C0 is V0. So E is basically V0 1 minus E minus T over tau, time constant. Okay, so when you apply step function, then voltage across capacitance become like V0. It's come down by exponential function. And if you apply square wave, then it's a step down here. The step down, go back up, and come down again, go back up. So it's kind of a triangle pulse against this. And this is E. Okay. Now we define the point that it's drop about 1/2 of the voltage V0, means this become half. Okay, so it's like a 1/2 equals E minus T tau. If you take a log 2 equals T0, not 0, T become, we call this time capital T, okay, capital T tau, okay, and this is 1, so T equals tau equals RC. So RC, we calculate RC, we can tell when the voltage become half. Okay, and for example, if C is 0.1 microfarad and R is 10k ohm, okay, so RC is 1 millisecond. So when you apply step function within 1 millisecond, the voltage change by half level. So it's going to be like half V0 point. This is like a 1 millisecond. Okay, so we demonstrate that in the hand-on electronics later. So this is a kind of characteristic. On the other hand, what happened to the current? The current actually this graph is wrong. Actually, this is a current, not E. The current initially flow and gradually becomes 0. The E, on the other hand, becomes like this, right? This equation. Yeah, right. Then go like that, and go like that, gonna go like that. Okay, yeah, and so this is 1/2 of v0. It's 1 millisecond for this time constant, and that's what we're going to get. Okay, now next transient analysis is inductor. Step function and R, L. So in this case, the voltage equals Ri plus L di dt. So in this case, step function is going to be v0. You take a derivative, it's going to be, you don't have to take a derivative in this case, right? This going to be again the exponential function. So what's happened is I equals if you don't take a derivative, v0 doesn't disappear, so it's not as simple as the capacitor case. In order to simplify, we make an equation for well, we can use Laplace transform. Laplace transformation solves this differential equation, and we use that for a little bit more complicated case. In this case, we know it's going to be the you modify this, divide by R, it's going to be the same format plus C0. And when you step up first time, this is going to be open circuit, so the E will be V0, right? I is 0, so T is 0, I is 0. That means V0 R plus C0 equals 0. So C0 equals V0 R negative. Okay. So we use this. I become V0 over R E T tau minus 1. In this case, tau is R over L. This is the time constant, okay? Actually, this is wrong. This should be L over R. Okay. Now, we choose the value like L is 1 millihenry, and R is 1 k ohm. So this is gonna be 1 microsecond. So within 1 microsecond, this is gonna come down about half. Okay, but the value of this inductance is not that accurate usually. So there will be some error here. Okay, we kind of assume the answer function is again exponent, and determine the constant. Okay, and it seemed to work out okay. As long as it's work out, you solve the differential equation. Right. Okay. So now E t is what? L di dt. Right. So it's going to be L R V0 and minus 1 over tau, right? Because you take a differential. So it's going to be this tau could disappear, minus V0 E minus t tau. Is that correct? Okay, so we made a mistake here somewhere. It looks like here the initial function, it doesn't work out with positive. It has to be negative, and that means this is positive and this is going to be 1 minus e, so this should be the current. Okay, we plug in. If you plug in to this, then it's work out. Okay, so in this case ET is going to be positive, so that makes sense. V0 E minus, again tau is time constant, so if L is 100 nanohenry and R is 10K, so it's produced same 1 millisecond. So we can do using same circuit arrangement. We can demonstrate this. Okay, that's good. So what happened is the voltage across inductance is going to be this way, and go up and come down and go up. Okay, so this is the time. You look at this waveform, it's same as the current for the capacitance, and the voltage of the capacitance look like that. The current for the inductance will be like that. So it's like they are complementary, capacitance and inductance. The transient waveform, the voltage for one looks like a current for another one, and current for one look like voltage for another one. Okay, that's a complementary. Now let's see, we are going to deal with a little bit more complicated case. R and the capacitance C and inductance L, and we apply the step function. So when you trigger this circuit, what's going to happen? This is E. Okay. In this case, E equals V0 minus Ri. Vt minus Ri. And I is, say, this is I. We split I1 and I2. The I1 is 1 over L E dt. And another one is C dE dt. Okay. Now we put together E's equation becomes a C. You multiply R to this E dt plus RC dE dt, and this is going to be constant V0 initial step-up function. This E is a time function, right? So Et so this current together plus the current times R is the voltage. The current together so this I1, I2 total current is I, and this total current I, and multiply by R is going to give this voltage plus E. Okay, so this voltage plus E is going to be total voltage. Okay, so let's take a Laplace transformation for this. S V0S, right? And you put together, you multiply S on the both sides and put together RC plus R over L Laplace transform V0. So Laplace transform voltage of the Laplace transform of the voltage is S square, and here we define 1 over LC square root as a omega. This is a frequency constant, so this is going to be omega square. Okay, so if you transform back to time domain, it's going to be okay. So this is actually the solution for differential equation. It's kind of hard to guess, so we use the Laplace transformation to figure out. So what's happened? This is sine wave. Where the hell does the sine wave come from? So when you apply the step function, it should be oscillate. So it's going to be oscillate at the frequency of W, which is 2 pi f. Okay, we should be able to demonstrate this. So we'll do that in the handle electronics. Does it oscillate forever? Actually, it's no, because there is a small resistor here in the inductance and the capacitance, and that resistor consume this oscillation energy. So oscillation become less and less if you leave it. But if you apply the square wave, then it's going to oscillate and oscillate back again. It's keep going. Okay, so let's see what happened. This is a way to make a crystal oscillator. The basic clock circuit for CPU or anything. You need to have a certain oscillation element with crystal, and the crystal generate stable of oscillation frequency. Okay, so let's look at the hands-on electronics here. Before we go to hands-on electronics, this is the 555 very well-known timer circuit, and timer circuit has basically threshold. This voltage increased by charge RC. You connect capacitor here. Okay, then there is a reset. After reset, this voltage increase, and it's go beyond a certain voltage. The flip-flop flip and turn on this transistor. When transistor turn on, then discharge. You connect the capacitor. Then this going to be discharged. Drop the voltage almost zero. Okay. Then once it's discharged, then this flip becomes off, and this off is going to start accumulating charge on the capacitance, external capacitance. So depend on what capacitance value you use, you can select the broad range of oscillation. Certain threshold voltage, this is a reference voltage, then suddenly discharge and charge, discharge. Okay, it's repeat this oscillation. So it's act as a timer. You define this time. When it start discharging, and once discharge, then it's become off. It start charging again, and it's repeat. So this is the timer IC chip. We're going to use this chip to make some jig and show you how it works. And you can change the resistor value externally, and resistor value is like potentiometer, right? Just turn the knob and make this time larger or smaller. Okay, so this is a simple IC chip available, very cheap. It's a couple dollars you can get it, and you can make your own timer. Okay, let's get back to hand-on electronics. To understand this timer circuit, that's a simplified version is you have the resistor and the capacitor, and you charge up capacitor. So this voltage go to comparator. It's a SR flip-flop. It's basically its comparator. Compare against this V reference. So when voltage goes up and it's exceed this V reference, so what's happened is this output voltage flip. It's actually we do this way. So it was negative and suddenly turned into positive. So what you do is this turn on, transistor turn on and discharge. Okay, as soon as it's discharged, it start accumulating voltage again. And this simple circuit is improved to have a few more consideration. That's the 555 IC chip. Okay, hand-on electronics time. Let's see. I'm gonna use a laser pointer, as because if I use a finger, you cannot see sometimes. Okay, the first circuit is very simple. We have 1K here, and that goes to this coil, 1 millihenry, and from there it's go back this the ground. Okay, and we set let's see if I can focus. As you see, voltage shoot up when the step function is given. And what's happened is this voltage supply square wave is also affected by inductance. So this is a common phenomena you have to know. It shoot up and it's come down. Right now it's 2 microsecond per grid. So this is 2, half about here. You see, it's come down to the half. It's coming down pretty fast. Okay. Okay, now the second setup is here. It's got the 10K ohm, and this 10K ohm go to this the 0.1 microfarad capacitor and go back. This is the ground. Go back. This is the ground. So if you look at, it's dropped right now the 1 millisecond, and 1 millisecond it's dropped about half from here to here. Okay, so this is the output, the voltage across the capacitor. Okay, so important thing is this voltage across capacitor and the time are related by exponential function. So using this, here's the 555. I did some construction, connect necessary capacitor here, and this potentiometer is to change the outside voltage, the resistors, so you can adjust the timing. Now if you press, you see LED light up. This LED lights up, and this time of LED lighting becomes short, and you can make it longer. Okay, what I'm doing here is this is 555 output. I use one IC chip, the counter, and it's countdown because timer is going too fast, and if you turn on and off LEDs that fast, you cannot see on and off. So what I did is I feed it to counter IC chip, and the counter IC chip make it the output of the IC chip is like, for example, it's count 1,000 times, then output goes to LED. And what happened is, once it's counted, it's trigger the reset of this 555 chip and terminate the operation. That means make it single pulse. The single pulse is hard to see in oscilloscope. You cannot see. Usually you need a square wave like this and see within this limit. Now, if you press this counting right now, and when it's finished, turn off. I change the resistor value by potentiometer, then it becomes much quicker. So you can adjust the timer, the length. Okay, so okay, that's all for this session.